In this video, we look at the final type of integral in calculus, the surface integral. Previously, we studied how to integrate over a two-dimensional curve. This was the line integral. And remember that there were two types of line integrals, a scalar function and a vector field. We'll now extend this notion to three dimensions. That is, we're now going to study how to integrate over a three-dimensional surface. And we call this kind of integral a surface integral. And just like with line integrals, there are two types, integrating a function and integrating a vector field. Now recall that when we were calculating line integrals, we needed to parameterize the curve of integration. Now the same is true for surface integrals. We need to parameterize the surface of integration. And the idea of parameterizing a surface is a natural extension of parameterizing a curve. We call a surface that is described by parametrization a parametric surface. Right? So, parametric surface is a surface in R3 whose points are described in a form like this. Right? The variables u and v are the parameters, and they vary in a region D in the UV plane called the parametric domain. We're going to look at two very important parameterizations next. Recall that when we studied cylindrical coordinates, we found that x was r cosine theta, y was r sine theta, and z is z, where r was the distance from the origin to the point xy in the xy plane, and theta was the angle that the line segment from the origin to the point xy makes with the positive x-axis. So it makes sense that the parameterization of a cylinder of radius r would be given by this. Also recall that when we studied spherical coordinates, we found that x was rho cosine theta sine phi, y was rho sine theta sine phi, and z was rho cosine phi, where rho was the distance from the origin to the point xy, theta was the angle in the xy plane that the line segment from the origin to the point xy makes with the positive x-axis, and phi was the angle that the line segment from the origin to the point xyz makes with the positive z-axis. So the parameterization of a sphere of radius r will be given by this. An easy parameterization, if the surface is the graph z equals f of xy, then we can just use this parameterization. Now let's suppose that a surface has a parameterization g of uv that is 1-to-1 on a domain D. We shall always assume that g is continuously differentiable, meaning that the function x of uv, y of uv, and z of uv have continuous partial derivatives. And so that's what it means to be continuously differentiable. Now in the UV plane, we can form a grid of lines parallel to the coordinate axes. These grid lines correspond under G to a system of grid curves on the surface. The horizontal and vertical lines through the point u0 v0 in the domain correspond to the grid curves G of uv0 and G of u0 v, respectively, that intersect at the point P equals G of u0 v0. Thus we can view partial G partial u of u0 v0 and partial G partial v of u0 v0 as vectors that are tangent to the surface S at the point G of u0 v0. And we now define the following tangent vectors. T sub u of u naught v naught is partial g partial u, and T sub v at u naught v naught is partial g partial v. We say that the parameterization g is regular if the normal vector to the surface at u naught v naught is non-zero, and the normal vector is given by T sub u crossed with T sub v. So that's what it means to be regular. Now consider the cylinder g of theta z, which is given by this parameterization. Then we get that T sub theta is this vector here, T sub z is this here, and so finding the normal vectors, we find that it's this. So the normal vector of a cylinder of radius r is given by this vector here, and it has a norm of r. If we now consider the sphere, given by this is what we'll get for T sub theta, this is what we'll get for T sub phi. Then if we go ahead and take a look at the normal vector, n, we get this value right here. However, this is inward pointing. So if we have outward pointing, this is what we're going to wind up with. Now, G sub 1 is the parameterization of the unit sphere. Right, that is, if we go back, G sub 1 is this bad boy right up here where r is equal to 1. Now, the magnitude of this normal vector would be that. Now, we let S be a surface given, or with a parameterization given here, over some domain D. Assume that G is continuously differentiable. We will also assume, for simplicity, that D is a rectangle, although the following argument can be extended to non-rectangular domains as well. We divide D into sub-rectangles, R sub ij, where I goes from 1 to big N, J goes from 1 to big N. It has horizontal width of delta U and vertical length of delta V. Now this division results in a corresponding division of the surface S into pieces S sub ij. Each S sub ij is a curved parallelogram. We now assume that the points P naught, Q naught, and S naught are at the corners of R sub ij, and that P, Q, and S are the corresponding points on S sub ij. Now, if delta U and delta V are small enough, then the curved parallelogram can be approximated as just a regular parallelogram with sides given by PQ, P, and PS. And recall that the area of a parallelogram with adjacent sides as vectors is the magnitude of their cross product. We can now use the approximations. PQ is G of U sub ij plus delta U, and then V sub ij minus this piece here. Well, this is approximately partial G partial U times delta U, and that is T sub U delta U. And also P sub S, using very similar logic, would be T sub V delta V. So we're going to get that the area of S sub ij is approximately the norm of T sub U delta U cross T sub V delta V, but delta U and delta V are constants, and remember, with cross product we can put the scalars anywhere we want. We're going to have to take the absolute value, but delta U and delta V are positive anyway, so the absolute value is not necessary. And the magnitude of TU cross TV is simply the magnitude of its normal vector. Now what this says is that the magnitude of n is a scaling factor that measures how the area of a small rectangle is altered under the map of G. Now the total surface area of S would be the sum of all these surface areas. That is, it's a double Riemann sum. It is approximately this double sum. Now as delta U and delta V as delta U and delta V approach 0, this converges to this double integral. So this piece right here is the surface area of S. So what this is saying is to find the surface area of a surface S, we need to find a parametrization of it first, that we find a normal vector, an outward pointing normal vector, take its norm, and integrate that norm over the domain of the parametrization. Now, all of that was preliminary work. Now we can define the surface integral, and we begin with a function. This is represented as the double integral over the surface S of xyz ds. Using the argument from surface area, we choose a sample point p sub ij, which is given by this, in each small patch S sub ij, and form this double Riemann sum. Then the limit of these sums is our integral, and that is formally stated. The surface integral of a scalar function f over a piecewise smooth surface S is simply the limit as the norm of the partitions of this double approaches 0 of this double Riemann sum. Now recall that the surface area was this right here, right, of that piece anyway. So we are going to use this to evaluate the scalar surface integral. If the surface is a parametric surface defined by D, then we write this double sum here as the double sum of f of G times the norm of n, delta U, delta V. That is a Riemann sum. It'll converge to a double integral, which is summarized in the following theorem. Right? G of UV is the parametrization of a surface S with parameter domain D. Obviously, G has to be continuously differentiable, one-to-one, and regular, except possibly at the boundary of D. Then to integrate the scalar function f of xyz over the surface S, we do the double integral over the parameter domain D of f evaluated at the parametrization times the outward pointing normal vector, the norm of the outward pointing normal vector, du dv. Some applications of the surface integrals. First, we have the mass or charge of a surface. So a surface with mass density or charge density delta of xyz in units of mass per area or charge per area has a total mass or total charge as the surface integral of delta. Let's consider this example. Find the total charge on a sphere of radius 5 centimeters whose charge density is given by delta of theta phi is 0.03 cosine squared phi measured in coulombs per square centimeter. Now, first we need a parametrization. Well, this is a sphere radius 5. So parametrization g of theta phi would be given by 5 cosine theta sine phi, 5 sine theta sine phi, and then 5 cosine phi. Right now, there's no restrictions, so both theta and phi will have their normal intervals. And so 0 to 2 pi for theta, 0 to pi for phi. And we already found that the magnitude of the normal vector here is r squared times sine of phi, so we have 25 times the sine of phi. So total charge of the sphere would be the surface integral over S of delta, which is 0.003 cosine squared of phi. We'll have the integral from 0 to 2 pi, have the integral from 0 to pi of 0.003 cosine squared phi times the norm, which is 25 sine of phi, d phi d theta. So we get 0.075 integral from 0 to 2 pi, integral from 0 to pi of cosine squared phi times sine of phi d phi d theta. This is 0.15 pi times the integral from 0 to pi cosine squared phi sine of phi d phi. This now gives us negative 0.15 pi over 3 times cosine cubed of phi. Now phi goes from 0 to pi, and we wind up with 0.1 pi, and that is of course measured in coulombs. Now if our surface happens to be a graph z equals g of xy, then recall that we'd have the parameterization x, y, g of xy. This would give this here. So instead of doing what we did in previous, we could just use norm of n as the square root here. Right, and then plug it in. This is how we would go ahead and evaluate it. Keep in mind this is only if the surface is the graph of a function g of x. We now go and look at the gravitational potential of a sphere. Now, the gravitational field f of g corresponding to any arrangement of masses is conservative. This means there is some function v sub g such that f sub g is equal to negative del v sub g, called the gravitational potential. So this V sub g is known as the gravitational potential. Now, recall that a field at a point P due to a mass m located at a point Q is given by this right here, where E sub r is the unit vector pointing from P to Q, and r is the distance from P to Q. Since this is an inverse square field, the potential function is negative gm over r, and r is just the absolute value of P minus Q. If there happen to be k point masses located at k points, then the gravitational potential is a summation. If mass is distributed over a thin surface S with mass density function delta, then we would pass this limit, or pass this through a limit as k approaches infinity, and that would result in this integral. Usually this integral cannot be evaluated explicitly unless the surface and mass distribution are sufficiently symmetric, as in the case of a hollow sphere of uniform mass density. We leave the actual evaluation of that integral for this case as an exercise, but this is what you should get when you evaluate it. So this is the gravitational potential of a hollow sphere. We now look at the surface integral of a vector field. These integrals represent flux, or rates of flow. So flux is simply a rate of flow through a surface. Because flux through a surface goes from one side to the other, we need to specify a positive direction of flow. This is done by means of an orientation, which is a choice of a normal vector n sub p at each point P of S, chosen in a continuously varying manner. Each point has two normal directions, so the orientation serves to specify one of the two sides of the surface in a consistent manner. The normal component of a vector field F at a point P on an oriented surface S is simply this dot product, which is of course the norm of f of P times cosine theta. Right, because little n is a unit vector, and theta is the angle between f and n. So the flux through or across the surface is given by the surface integral of f dot ds, which can be written as the surface integral of f dot n ds. And this is the Greek letter capital Phi. An oriented parametrization is a regular parametrization whose unit normal vector is this term right here. So this is a unit normal, right? So that is, of course, why up here we had the norm of this being 1. Now recall that ds was this bad boy right here. So the flux now becomes f of g dotted with n of g times the norm of n du dv. And of course that double integral is over the domain of the parametrization. But n of g can be written as this. And of course, it does not matter where we put the scalar, so we can combine these two right here. And of course, the norms are going to cancel out, and we're left with this. This would remain valid even if n is 0 at some points on the boundary of the parameter domain D. If we reverse the orientation, we simply replace n with this negative n. And this gives us a way to evaluate the vector surface integral. Imagine dropping a net into a stream of flowing water. The flow rate is the volume of water that flows through the net per unit time. Let V be the velocity field. Now, at each point P, V of P is the velocity vector of the fluid particle located at P. Suppose first that this net is a rectangle of area A, and that V is a constant vector field with value V naught that's perpendicular to the rectangle. The particles travel at a speed norm of V naught, measured in meters per second. So a given particle flows through S within a 1 second time interval if its distance to S is at most norm of V naught meters. In other words, if its velocity vector passes through S. Thus, the block of fluid passing through S in a 1 second interval is a box of volume norm of V naught times A, and the flux is the norm of V naught times A. If the fluid flows at an angle theta relative to S, then the block of water is a parallelepiped of volume A times norm of V naught times cosine theta. If n is a vector normal to S of length equal to the area of A, then we can write the flow rate as V naught dotted with n. In the general case, the velocity field V is not a constant, and the surface may be curved. To compute the flow rate, we choose a parameterization G, and we consider a small rectangle of size delta U times delta V, by delta V I should say, that is mapped to G by a small patch S naught of S. For any sample point G equal G of U naught V naught in S naught, then this vector here is a normal vector of length approximately equal to the area of S naught. This patch is nearly rectangular, and so we get this now as an approximation for flux. The total flow per second is the sum of the flows through all the small patches. As usual, we would pass this through a limit to get the following. For a fluid with velocity field V, the flow rate across the surface is given by this surface integral. So the flow rate is simply the surface integral of V dot ds, or the flux of the velocity vector across S. Right, so let V be this vector here, measured in centimeters per second, of a fluid in R3. We wish to compute the flow rate upward through the upper hemisphere of the unit sphere centered at the origin. So if we were to try and draw it, right, this is the upper hemisphere of a unit sphere. So we're measuring the upwards flow rate. So it's moving in this direction. Now what we need is parametrization. Well, it's a sphere. Unit sphere, to be exact. So the parametrization will be cosine of theta, sine of phi, sine of theta, sine of phi, cosine of phi. Now theta remains unchanged. It'll be from 0 to 2 pi. However, since we're dealing with the upper hemisphere, phi will only go from 0 to pi. Note that this means that the normal vector is sine of phi times this g. Now, plug this in. The flow rate is the surface integral v dot ds. This will now be the double integral over the domain D, which is up here, of v evaluated at g dotted with n. Then we're going to be left with d phi d theta. What this becomes, integral from 0 to 2 pi, integral from 0 to pi over 2. We now have to do v of g. That'll give us cosine squared theta sine squared phi plus sine squared theta sine squared phi 0 cosine squared phi. That gets dotted with sine of phi times g1. Right, and then that's d phi d theta. Now, when we do the dot product, we'll be left with sine of phi times cosine of theta sine cubed of phi plus cosine cubed of phi d phi d theta. Distribute that through, we'll be left with cosine of theta sine to the fourth phi plus sine of phi cosine cubed of phi d phi d theta. Now, the period of cosine of theta is 2 pi, so if we go about integrating from 0 to 2 pi, that term will just integrate out to 0. So really, this is the same as doing this. Integral from 0 to 2 pi, integral from 0 to pi over 2 of sine phi cosine cubed phi d phi d theta. This will of course be 2 pi times from 0 to pi over 2 sine of phi cosine cubed of phi. This will be 2 pi times the integral. We can use u sub cosine to the fourth phi over 4. Phi goes from 0 to pi over 2. Right, this, of course, should be a negative here. And this will leave us with pi over 2 cubic centimeters per second. Now recall that when we first looked at vector fields, we introduced Maxwell's equations in differential form. Well, here we have them in their integral form. Again, these say the exact same thing as the differential forms. These are just written as integrals. And with that, we conclude this video on surface integrals. There's only 3 more things left to cover that will be done in 2 videos. We have to cover the 3 theorems of vector analysis: Green's theorem, Stokes' theorem, and divergence theorem.